We have been picturing black holes all wrong. The mathematical model we typically use contains a fatal flaw, one that effectively deletes reality itself. For decades, we relied on Albert Einstein's general relativity. In this classical view, a black hole relies on two distinct features. There is the event horizon, a mathematical boundary marking the point of no return, and at the exact center, there is the singularity. General relativity dictates that every ounce of a black hole's mass is crushed into that singularity. It is an infinitely dense, completely dimensionless speck where mass exists in zero space. Physicists accepted this infinite crush of matter as absolute truth for most of the 20th century, but packing an entire star into a tiny, dimensionless point creates a massive mathematical glitch that threatens our entire understanding of the cosmos. The glitch became apparent in the 1970s when Stephen Hawking proved that black holes actually emit a very faint energy. This energy is known as Hawking radiation. Because a black hole is constantly leaking this radiation out into space, it is slowly losing mass. Given enough trillions of years, a black hole will eventually evaporate completely into nothingness. This triggers an enormous conflict with quantum mechanics. Quantum physics operates on one unbreakable rule. The precise data making up the universe, quantum information, cannot be destroyed under any circumstances. Hawking calculated that the radiation leaking out of a black hole is completely random. It carries zero data about the objects that originally fell in. So if a black hole evaporates completely, leaving behind nothing but random noise, all that original data is permanently erased. This is a catastrophe for our understanding of reality. Quantum equations rely on the ability to run time backward and forward. If you know a particle's current state, you can determine its entire history. If a black hole permanently deletes that data, that predictability vanishes, and the math used to describe every atom in existence ceases to function. To rescue quantum mechanics, theoretical physicist Samir Mathur proposed a complete rethinking of what sits at the center of that gravity well. Mathur used string theory, which argues that the universe is not built from hard, point-like particles. Instead, everything is composed of microscopic, one-dimensional, vibrating strings of energy. Apply this logic to a collapsing star. As gravity bears down, these fundamental strings are compressed, but they never crush down into a single dimensionless speck. Instead, the extreme gravity forces the strings to fuse. They weave together into a hyperdense, highly chaotic ball of yarn. The resulting tangle exerts an immense outward pressure that actively pushes back against the crush of gravity. This outward push stops the collapse entirely. The impossible empty void and the infinitely dense dot are gone, replaced by a solid, ultra-dense object. Physicists call it a fuzzball. Unlike the classical model, the fuzzball hypothesis completely eliminates the singularity. It also gets rid of the event horizon. There is no mathematical point of no return floating in empty space. Instead, a fuzzball has a physical, boiling surface of interwoven strings that sits exactly where the event horizon used to be. When matter falls into this object, it does not disappear into a pit. The new particles simply stretch out and add their own strings to the giant tangle, causing the entire sphere to grow slightly larger. The fuzzball fills the space previously occupied by the empty event horizon, replacing the void with a solid, vibrating mass of strings. It functions as a sphere of ultra-dense matter, the final state of a collapsing star that gravity simply cannot crush any further. Because the fuzzball has a physical surface, it solves the information paradox. As Hawking radiation is generated, it interacts directly with that boiling outer layer of strings. The departing radiation absorbs the precise vibratory patterns of those strings, encoding the data. The quantum information of whatever fell into the black hole is never destroyed. The fuzzball scrambles the data, but it safely leaks it back out into the universe piece by piece over trillions of years. We do not yet have the telescope technology to zoom in on a black hole's surface and see if it's smooth spacetime or a fuzzy ball of cosmic yarn. As our best photographs show, our view is still incredibly blurry. But the math of string theory provides a highly elegant answer. The universe does not arbitrarily delete its own history. It just tangles it up, keeping the data intact and protecting the laws of physics in the process.